as you recall from our last video, we started doing the work for our demo. We did all the calculations as to what our Q or our delta H would be for this reaction and how we would make this combustion of the alcohol less exothermic or less reactive. And we decided if we mixed water in combining those reactions, we would absorb some of the energy given off by the combustion of the isopropyl alcohol by the vaporization of the water. So in this beaker, I have 50 milliliters of distilled water and 50 milliliters of isopropyl alcohol, which was the combination we worked out in the problem set in the previous video. So now I'm going to go ahead and take this cheesecloth here, and I'm just going to soak it in the mixture. Alright, so as we take it out of the beaker here, we're going to drain off the excess. We don't need to cause, huge fire. Go ahead and shake them on out. Around by the middle. Alright, so now we have our cloth soaked in our 50% isopropyl alcohol mixture and 50% water. And I'll hold it over the flame. And as we would expect to see, we see it surrounded by a flame. You can see the blue surrounding the towel, but the towel itself is not on fire. As you see the flames growing, you're seeing the combustion of the isopropyl alcohol. Alright, that's good. Go ahead. You can see that it's not even charred. Yay! The towel didn't burn. We can assume then that extra energy given off by the combustion of isopropyl alcohol was consumed in the vaporization of water and transferred to the air around the reaction. If we had been using a calorimeter, we could have quantified this heat transfer and therefore calculated the Q of the reaction. These kinds of problems are really important in real-life application as well. For instance, the West Fertilizer Company in Texas decided to store massive amounts of ammonium nitrate. Well, in the presence of heat, ammonium nitrate is extremely explosive. So if you imagine tankfuls of this coming in contact with heat, well, they managed to level the entire town. However, if they had done a simple calorimetry problem, they could have avoided this. Let's go ahead and look at one now.
Alright, so here's the 411 on what happened at the West Fertilizer plant. I found this from the U.S. Chemical Safety Board in its preliminary investigations. Basically, they found that 30 tons of ammonium nitrate were being stored at this fertilizer plant. It was being stored inside of wooden bins inside of a wooden warehouse. In addition to this, there were other flammable materials around, such as ammonia and PVC pipe. So basically, there was one spark, which created a huge fire in the detonation of ammonium nitrate. So I want to go ahead and look at a couple problems working with this idea. So, in the presence of heat, ammonium nitrate begins to melt at 169.9 degrees Celsius. It then begins to decompose, and then finally we have a detonation at 300 degrees Celsius. So let's go ahead and calculate the energy of each step and figure out where our total energy is that we're working with for the West Fertilizer plant. Alright, so step number 1 is that the ammonium nitrate melts. It goes from a solid form to a liquid form. And if you remember our table from the first video, as we're doing this phase transition, we're going to use the heat of formation. Okay, so I went ahead and looked this value up online. The heat of formation for ammonium nitrate going from a solid to a liquid is 5.44 kilojoules per mole. And remember, this is happening at 169.9 degrees Celsius. Okay, so now we're just going to do a bunch of stoichiometry. We're working with 30 tons of ammonium nitrate, and we multiply this by 907.185 kilograms per ton, multiply this by 1,000 grams per kilogram, and then we multiply it by the molar mass of ammonium nitrate, or 1 mole per 80.052 grams. And we get that we're working with 3.39 times 10 to the 5th moles. Okay, so we can plug this in and use that for our heat of formation. So 5.44 kilojoules per mole times the 3.39 times 10 to the 5th moles we're working with equals a total of 1.85 times 10 to the 6 kilojoules. And notice this is positive, so at this point we are endothermic, we're absorbing energy still. Okay, so now we move on to step 2, which is decomposition. So here we have our liquid form of ammonium nitrate, as it's already melted, going to water vapor and dinitrogen oxide gas. So we have our traditional calorimetry equation, where Q is equal to the specific heat, which in this case is negative 139.32 joules per degree mole. Now notice this is in degrees, so it's in degrees Celsius, which is not common to see. Degrees Celsius is not an SI unit, but we're going to go ahead and use it for this calculation. And then we have our mass, or our N, which is 3.39 times 10 to the 5th moles. And notice I'm working in moles, same as my specific heat. Okay, and then my delta T, which is equal to TF minus TI. And remember from that first slide we said, okay, so detonation occurs at 300 degrees Celsius, melting occurs at 169.9 degrees Celsius. So we're going to use these as our TF and TI, which equals 130.1 degrees Celsius. So I plug all of these into my formula, and I end up calculating a Q of negative 6.14 times 10 to the 6 kilojoules. And this is a pretty high value. Notice that this is exothermic. We're working in a negative, so we're starting to go ahead and give off energy. Okay, so step 3 is detonation, and this occurs at 300 degrees Celsius. I found that the heat of explosion for ammonium nitrate is negative 1,592 kilojoules per kilogram. So I go ahead and use my stoichiometry tools again and calculate that 1,592 kilojoules per kilogram times 907.185 kilograms per ton times 30 tons equals a heat of explosion of negative 4.33 times 10 to the 7 kilojoules. And so that's pretty high. So grand total, drum roll, we have my heat of formation, which is endothermic, of 1.85 times 10 to the 6 kilojoules. My heat of decomposition, so the Q of reaction there, which is negative 6.14 times 10 to the 6 kilojoules. My heat of explosion, which was negative 4.33 times 10 to the 7 kilojoules. Sum them all up, and we end up with negative 4.76 times 10 to the 7th kilojoules. And that's quite a bit. So my question for you guys would be, what about ammonium nitrate in water? What if there had been sprinkler systems in place in the warehouse before this had even occurred? Would it have made a difference? So we're going to go ahead and look at a calorimetry problem and then apply it to this question. So the calorimetry problem is this. When a 4.25 gram sample of solid ammonium nitrate dissolves in 60 grams of water in a coffee cup calorimeter, the temperature falls from 22 degrees Celsius to 16.9 degrees Celsius. Calculate delta H in kilojoules per gram of ammonium nitrate for the reaction. And it says here that we can assume that the specific heat of the solution is the same for that of pure water. That'll be helpful. Okay, so step number 1 is to write out the reaction. And here we have solid ammonium nitrate going to ammonia aqueous form and nitrate in its aqueous form, so breaking down to those ions. Next is to set up the equation for Q of reaction. So we have to have our two different parts. Q of reaction is equal to the negative summation of Q of solution plus Q of cup. Okay, so now we're going to go ahead and break those down, or solve the different pieces of the larger equation. So we'll start with our Q of solution, which once again equals our specific heat times the mass times change in temperature. And in this case it says we can assume that the specific heat is that of equal to pure water, which is 4.184 joules per gram Kelvin. So notice what units we're working in. We're working with grams, so that means our mass also has to be in grams. And here we need to add in 60 grams for the water and 4.25 grams of that ammonium nitrate. My change in temperature, so my T final is 16.9 degrees Celsius, whereas my T initial is 22 degrees Celsius. So we're going to go ahead and decrease in temperature, which is equal to negative 5.1 degrees Celsius, or negative 5.1 Kelvin. Okay, so I can plug all these values in and calculate a negative 1.36 kilojoules. Okay, so now I'm going to solve the different pieces of the larger equation, still doing that, and now I can move on to my Q cup. And here we actually get to assume that Q cup is equal to 0 kilojoules because we were not given the specific heat for it or any other data. Okay, so that means Q of reaction, we can plug this into that larger equation where negative Q of solution, and we have to divide this out by the total grams that we had of ammonium nitrate. So we have what is going to equal positive 1.36 kilojoules divided by 4.25 grams of solid ammonium nitrate, and this equals 0.32 kilojoules per gram of ammonium nitrate. So, how much energy could be absorbed if the 30 tons of ammonium nitrate from the plant were soaked in water then? So we can go ahead and use our stoichiometry. We just calculated that when placed in water, ammonium nitrate absorbs 0.32 kilojoules per gram. And then we multiply this by 1,000 grams per kilogram, 907.185 kilograms per ton, times 30 tons, and I end up with 8.71 times 10 to the 6 kilojoules. And notice it's positive, so that's endothermic. That's the amount of energy we're absorbing rather than giving off. So basically, that's quite a bit of the negative 4.76 times 10 to the 7 kilojoules that was given off by the explosion of ammonium nitrate. So I bet they were wishing they had sprinklers in place now. And that, my friends, is why we should give 2 kilojoules about calorimetry.